You might think soap is a simple substance made from animal fat and lye that has been around since ancient times. And that's not wrong. But there's more to this humble cleaning agent than meets the eye. In fact, there are some surprising hidden science stories behind how it's made, why it works so well at cleaning, and what exactly we mean when we say it as a soap. So let's get sudsy and dive into the hidden science of soap. When people talk about the history of soap making, they often point to a 2,800-year-old Babylonian record of a kind of soap being made from animal fat and ashes. And while these days we know better than to use ashes, we still make soap in much the same way. In fact, if you have a bar of soap and a chemistry set, you can make soap for yourself. The basic recipe is pretty simple. Take 12% of the weight of the soap you want to make in lye and mix it with an equal amount of water. Then add 88% of your chosen oil or fat and mix that up really well. After boiling the mixture for a little while, you end up with something that looks like cold cream. Let it cool and solidify, and voila, soap. But what's actually happening during those chemical changes? To understand what's going on when you make soap, you need to learn a little bit about triglycerides. Triglycerides are the primary component of most fats and oils. Each one consists of a molecule of glycerol, which has 3 long hydrocarbon chains attached to it. These chains vary in length and in the types of bonds between their carbon atoms, which affects how liquid or solid a particular fat or oil will be at room temperature. When you combine an oil or fat with lye, you break the bond between the glycerol and the hydrocarbon chains, and the lye binds with the chains instead. What you're left with are molecules of soap, also called sodium or potassium salts of fatty acids, and a molecule of glycerin. Since the density of the soap molecules is higher than that of glycerin, the glycerin separates out on top, which is why cold cream is ever so slightly yellow in color. Once it solidifies into soap, it floats on top of the remaining liquid. That's why it's important to boil the mixture for a little while before letting it cool. If you don't, the glycerin will end up trapped inside the soap, which makes a softer, less durable bar. Boiling it gets rid of excess water and allows the glycerin to escape. As for why soap made from this basic recipe cleans so well, it has to do with the molecular structure of soap itself. Soap molecules have 2 distinct parts, a hydrophilic head that loves water and a hydrophobic tail that hates it. Since the heads love water, they tend to gather near any body of water, like on the surface of a puddle. And since the tails hate water, they tend to hide from it. This means that when you put a soap molecule on a greasy surface, its hydrophobic tail dives into the grease while its hydrophilic head stays in the water. Basically, the soap molecules act as a sort of mediator between the grease and the water, helping the water lift the grease away. This process is known as emulsification, since the soap is emulsifying or combining the 2 liquids that normally repel each other. It's worth noting that this isn't how soap interacts with every type of stain. For example, some dyes actually become more attracted to fabric fibers once they've been treated with soap. So always test a small, inconspicuous area first before treating a whole garment. Now, when we say that soap is made from animal fat and lye, we're referring to the traditional method of making soap described above. But nowadays, soap comes in many different forms and is made in a number of different ways. One popular type of soap is so-called transparent soap, which can look like a clear piece of glass rather than a cloudy bar. To make transparent soap, soap makers start with a clear, almost colorless oil called coconut oil. They also use a special technique to get the water and lye mixture, it's also called the alkaline solution, into the oil without creating too many bubbles. Bubbles introduce air into the soap, which can cause cloudiness in the final product. So the alkaline solution is carefully dripped into the oil while it's being stirred, which helps prevent bubble formation. After boiling the mixture, the soap maker pours it into a mold and lets it sit until it hardens. The finished soap is clear, but it's still a little opaque. It's to make it more transparent, the soap maker puts it in a special machine that heats it and pulls out any unemulsified oil. The result is a clear, almost crystalline piece of soap. These days, many soaps contain ingredients other than just soap and glycerin. Some soap makers add extra oils for conditioning, like coconut oil or olive oil, while others incorporate exfoliants such as ground oatmeal, baking soda, or crushed nutshells. Some people even make liquid soap by dissolving a bar of soap in warm water. Whatever form it takes, though, all soap is made the same way. Right. Traditional bar soap is just solid. Liquid soap is just bar soap dissolved in water. Those little beads you sometimes see in hand soap are just bits of solid soap suspended in a liquid. Then there's an interesting type of soap that's not technically soap at all. We're talking about synthetic detergents. Synthetic detergents, or just detergents, are cleaning agents that are chemically similar to soap, but don't require animal fat for their production. Instead, they're made from petroleum, which is why they're sometimes called petrochemicals. The manufacturing process starts with a hydrocarbon, which is a molecule consisting only of hydrogen and carbon atoms. Manufacturers subject the hydrocarbon to a series of chemical reactions that add oxygen, hydrogen, and sodium atoms to it. The end product can be used just like soap, to emulsify dirt and oil in your laundry or on your hands. Detergents were invented in the early 20th century to provide an alternative to soap for people who didn't want to use animal products. But today, we use them mostly because they have some advantages over soap. For one thing, they work just as well in cold water as in hot water, and they don't react with other substances in the way that soap can, meaning they won't turn your bathtub into a skating rink when you run the tap. A big downside of detergents, however, is that they aren't biodegradable. Many of them persist in the environment for years, harming wildlife and getting into our food supply. Because of these effects, manufacturers have started making biodegradable detergents from plant-based chemicals, like coconut oil and cornstarch. While these eco-friendly detergents may not lather as much as traditional soap, they're an improvement over their petroleum-based counterparts. So next time you go to wash your hands, take a moment to appreciate the hidden science of soap. Whether it's made from petroleum, plant products, or animal fat, soap is a truly remarkable substance that's helped keep us clean for thousands of years. Just remember not to use ashes. Speaking of remarkable substances, there's one major organ in your body that's pretty remarkable, your brain. And Brilliant has a course all about it. Their Neuro course for everyone covers the basics of how neurons work and what happens when things go wrong. You'll explore how your brain processes sensory information, what causes neurological disorders, and how brain injuries affect the way we think and move. Plus, after taking this course, you'll be equipped with the knowledge to answer all sorts of questions like, why do I have dreams? How does music affect my brain? And what determines whether I'm a morning person or a night owl? You do need to be a neuroscientist to appreciate the amazing science that goes on inside our heads. I'll sign up with the link below and get ready to unlock all the secrets of your brain. The first 200 of you to sign up will get 20% off Brilliant's annual premium subscription. And Brilliant has thousands of lessons on science, math, and engineering. So after you finish learning about your brain, you can move on to something else you've always wanted to understand. Thanks to Brilliant for supporting this video.